Welcome to For the Love of Books podcast.
All right, let's do this. Today, we are tackling an absolute giant, Stephen Hawking's A Brief History of Time. I mean, this is the book that completely changed how a generation saw the universe. So, what's our mission? We're going to try to boil down its incredible, mind-bending ideas into just a few minutes. Yeah, it's a huge task, but let's jump right in. And right away, Hawking just hits you with the two biggest questions you could possibly ask. I mean, think about it. These aren't just for scientists in a lab. These are the questions that people have been staring up at the night sky and asking for thousands of years. This is what it's all about. You know, to really get where we are today, you have to appreciate how far we've come. For ages, we thought we were the center of everything, that the whole universe revolved around us. Then, bam, Newton comes along and gives us gravity, these rules that govern the heavens. But then came Einstein, who didn't just change the rules, he flipped the whole game board over with his ideas about space-time and relativity. Okay, so let's get into those new rules. And I'm not kidding when I say Einstein rewrote the cosmic playbook. He gave us a totally new way to understand the very fabric of reality. And it all started with this one stunning discovery. A guy named Edwin Hubble pointed his telescope at the sky and realized that all the distant galaxies, they're all flying away from us. Now, just think about that for a second. If you hit rewind on that motion, what does it mean? It means everything, you, me, every star, every galaxy, must have started out squished together in one single, unimaginably hot and dense point. And that, right there, is the big idea behind the Big Bang. So what is this stuff that the universe is made of? Einstein told us it's something called space-time. Space and time aren't separate things. They're woven together into a single four-dimensional fabric. The best way to picture it? Imagine a giant trampoline. Now, if you put a bowling ball in the middle, it creates a dip, right? That's exactly what planets and stars do to space-time. They warp it. And that warping, that curve in the fabric, is what we feel as gravity. It's not a mysterious force, it's just the shape of space-time itself. And here's where it gets really, really weird. One of the craziest results of this is that time isn't constant, it's relative. So if you're an astronaut zipping around in a super fast rocket, time for you would actually tick by slower than it does for all of us back here on Earth. You'd come back a little bit younger than you would have been. It's a real proven effect. The faster you move through space, the slower you move through time. Absolutely mind-bending. Okay, so Einstein's rules are fantastic for the big stuff. Planets, stars, galaxies. But what happens when we zoom way, way down to the world of tiny particles? Well, we enter a whole new world with completely different rules, the world of quantum mechanics. And its most famous rule is the uncertainty principle. This basically says there's a fundamental limit to what we can know. You can know where a particle is or where it's going, but you can never, ever know both perfectly at the same time. And it's not because our tools aren't good enough. It's because reality itself is just fuzzy at that level. So, where do these two great theories, Einstein's big-scale relativity and the weirdness of quantum mechanics, finally meet? Or more like, where do they collide? The answer is in black holes. These things are the most extreme environments in the entire universe. They're the ultimate laboratory for pushing the laws of physics to their absolute breaking point. At the heart of every black hole is its most famous feature, the event horizon. You can think of it as the ultimate point of no return. It's not a wall or a surface. It's more like the edge of a waterfall in space-time. Once you drift past that edge, the current is too strong. Nothing, not a spaceship, not a planet, not even a beam of light, can ever escape. And for the longest time, that's what we thought. Black holes were the universe's perfect prisons. Whatever goes in, stays in, forever. End of story. But then, Stephen Hawking entered the picture, and by using the strange rules of quantum mechanics, he added a twist that nobody saw coming. And this is maybe his greatest legacy, Hawking radiation. He figured out that thanks to some quantum weirdness happening right at the edge of the event horizon, black holes aren't perfectly black. They actually leak particles out into space that glow ever so faintly. This means they have a temperature, and if they're leaking energy, they're losing mass. And if they're losing mass, it means that over incredible, mind-bogglingly long periods of time, a black hole can completely evaporate and vanish. They're not eternal after all. Wow. This leads us to another one of those deep, fundamental questions that we all feel but can't easily explain. Why does time only seem to flow in one direction, right? We remember yesterday, but we don't remember tomorrow. You can drop a glass and watch it shatter, but you'll never see a pile of shards jump back together to form a glass. Why is that? Why is there an arrow of time?
Well, Hawking connects it to three things that all point in the same direction. First, there's the cosmological arrow, the simple fact that the universe is expanding. Because of that, we have the thermodynamic arrow. The universe is always getting messier, more disordered. The scientific term is entropy, but you can just think of a clean room that naturally gets messy over time. And here's the kicker. Our psychological arrow, the feeling that time moves forward, is tied directly to that. We create memories, which makes our brains more ordered in a universe that's getting more disordered. We remember the past because it was less messy than the future will be.
Okay, so here's the big problem facing physics. We have general relativity, which is perfect for describing gravity in the universe on a huge scale, and we have quantum mechanics, which is perfect for describing the tiny world of particles. Both work beautifully in their own realms. The problem? They fundamentally disagree with each other. They speak different languages. So the holy grail, the ultimate goal, is to find one single theory that can unite them. Now, any theory of everything has to be able to explain all four of the fundamental forces of nature. You've got the strong and weak nuclear forces that operate inside atoms. You have electromagnetism, which governs light, electricity, chemistry, basically everything you interact with daily. And then you have gravity, which, and this is kind of amazing, is by far the weakest of them all, yet it's the one that shapes the entire universe. A final theory needs to explain all of these from a single, elegant idea. So, can we actually do it? Is it even possible to write down a single equation, a single set of rules that explains everything from why an apple falls from a tree to what happened in the first instant of the Big Bang? This is the question that drove Stephen Hawking for his entire life. You see, a unified theory would be the ultimate prize. It would finally merge relativity and quantum mechanics. It would give us the tools to truly understand what's happening inside a black hole, or what the universe was like a fraction of a second after it was born. There are candidates out there, like string theory, but the search is definitely still on.
But, and this is where Hawking takes it to another level, finding that final theory would lead us to an even deeper question. It's one thing to know how the universe works, to have all the equations. It's another thing entirely to ask, why? Why is there a universe at all? Why these rules and not some others?
And that brings us to this powerful, unforgettable quote. For Hawking, the search for a complete theory of the universe wasn't just about the math. It was about understanding our place in the cosmos. It was a quest to answer the deepest why of all, and in doing so, to finally comprehend the grand design of reality itself.